This problem is a little bit tricky because we have a semicircle, I guess you call it a semicircle of radius r, so it's half of a circle, and inside, and it's made out of some metal, some wire through which current can flow. And in the center of that semicircle is another semicircle, but of smaller radius, little r. And everything here is fixed, but the little r, this small semicircle, is allowed to rotate around this vertical axis. I don't want to draw a line connecting these two. It rotates around this axis, let's see, actually in this direction. And then this is the initial stage, and then this is the final, when this small semicircle has rotated to be straight up and down. So it goes from here to here. So this wants to know, the question asks, determine the average current, if any, induced in the coil, the whole coil, as a result of going from this orientation to that orientation. Okay, so let's look at Faraday's law for a second. The induced EMF is equal to negative times the time rate of change of the magnetic flux. Well, that doesn't give us current, but from Ohm's law, we know that is equal to the current I through the resistance R. We also know here N is equal to 1 because it's just one loop. It's not double going round and round. So I'll plug in 1 and I'll solve for I. So I have the current is negative 1 over R d phi b dt. Well, okay, so let's expand it further. Negative 1 over R, we just have that extra 1 over R added to convert from EMF to current. d dt times the flux, which is BA cosine of phi. So the question is here, what is varying and what is fixed? Well, the magnetic field is, we're told that it is out of the plane, and it's fixed. It's the same the whole time. So this is fixed. Now it seems like something is spinning here. So the orientation is going to change. But the question asks us for the average current. So the thing is, yeah, we could deal with the area, but then you're going to have two fluxes. You're going to have the flux of this big one, which is going to stay fixed, and then you have to subtract out the flux of this little one, which is varying with some, it's varying with cosine of phi. But the problem's a lot simpler than that, because if you just want to know what the average current between this section and that section is, all you have to do is look at, well, what is different from here to here? The area is changing. So I'm going to say that the phi is effectively fixed, and so equals 1. Cosine phi equals 0, cosine of 0 equals 1. Now that's not really the case. I'm just making the problem easier, because the orientation between the area normal vector and the magnetic field is, well, it is fixed for the bigger loop, but it's not fixed for the little one. It's spinning around, so it's changing. But we just want to know from here to here, what is the average induced average current. So I'm going to say this is effectively fixed, whereas this is the angle of the area normal vector of this whole effective loop, which is the same. It's just it's been pulled out a little bit and the area has changed. I hope that makes sense. I mean, you could work it either way. So negative 1 over R B, and remember that goes to 1, so I can just drop that out, d A dt. But again, this is actually, I shouldn't have put average here, because this is not the formula for average. The average current is just negative 1 over RB times change in A over change in T. Remember, we've gone through this several times. If you have some, in this case, the area is increasing. So if we're looking at the change in area, if it goes through some crazy kind of path to get to, you know, the final, A final, well, then you would have to differentiate that function. We don't have that function, but what we can say is we can look at the average change is given by the slope of the straight line, which is just change in A over change in T, which is negative B over R times A final minus A initial over delta T. So what is A final? Well, A final is easy. It's just pi capital R squared. I'm sorry, over 2, because it is because it's only half the circle. Initially, A initial is pi R squared over 2 minus pi little r squared over 2, because you have to subtract that out in the beginning. So I'll just write it down here. Delta A is equal to A final pi r squared over 2 minus A initial pi r squared over 2 minus pi little r squared over 2. And we can simplify that, I hope. So this minus this is 0. Then you're left with just a change, an increase of positive pi little r squared over 2. Okay, but we haven't found delta t. We can take this and dump it in up here, but we haven't found delta t yet. So in order to find delta t, let's look back at our kinematic equations. So our final location is equal to our initial location plus velocity times the amount of time you travel plus 1/2 at squared, correct? Do you remember that at all? If we put that in angular terms, the final angular position is equal to the initial angular position plus angular velocity times time plus 1/2 times angular acceleration times time squared. Well, in this case, there's no acceleration. It's a constant angular velocity, so that equals 0. We can call the starting point 0. So the final angular position is equal to omega times t. That means t, and again, this is applied delta t, is equal to the final angular position over omega and the final angular position equals pi over 2 because it's going from 0 to pi over 2. So I can plug that in. Delta t is equal to pi over 2 omega. So the result then is I average is equal to negative b over r times pi little r squared over 2 over pi over 2 omega. So I flip this fraction and I end up with negative b over 2 times the pi's cancel out. The 2's are going to cancel out. So that will equal negative b r squared omega. I believe that's it. B r squared omega. So the bar can mean average is, and if I just want to get the absolute value of it, I don't care about the direction. It would be b r squared omega. so this equals 0.35 Tesla times r squared, which is 0.20 meters, times omega, which is 1.5 rads per second. Do the math and you end up with, what is that, about 0.84? 0.84